Semiconductor past paper questions. 2015 paper 1, question 19. We have 3 statements about energy bands and different materials, and we need to decide which ones are correct. Statement 1, metals, the highest occupied energy band is not completely full. That's true. The highest occupied energy band is the conduction band, and that's only partially full. Statement 2, in insulators, the highest occupied energy band is full. That is also true. In insulators, the highest occupied energy band is the valence band, and at 0 Kelvin, that is full. Statement 3, the gap between the valence band and conduction band is smaller in semiconductors than in insulators. That is also true, which means E is the correct answer. Statement 1, 2, and 3. 2016, section 2, question 12b, part 1. Some cars use LEDs in place of filament lamps. An LED is made from semiconductor material that has been doped with impurities to create a p-n junction. The diagram represents the band structure of the LED. So we can see on the diagram, here is our p-type material, where we have majority positive charge carriers as holes within the valence band. Here is our n-type material, where we have majority negative charge carriers, that is electrons, in the conduction band. Here is the junction in between. So we have holes from the p-type material going into the junction, and we have electrons from the n-type material going into the junction. And it's the recombination of those two things here, which is where we have the emission of photons. Question part 1 says a voltage is applied across an LED so that it's forward biased and emits light. Use band theory, explain how the LED emits light. So we can see here from the SK marking solutions, a voltage is applied. That's in brackets, which means it's not essential. What we really want is electrons move towards the conduction band of the p-type away from the n-type towards the junction. Electrons drop from the conduction band to the valence band. Remember, the conduction band's a higher energy level, so we move from a higher energy level in the conduction band to a lower energy level in the valence band. We have a difference in energy. That energy is released as photons. So the key bits of information here is that electrons move towards the conduction bands of the p-type or away from the n-type. This stuff here. Electrons move, they drop down in energy level, and photons are emitted. (2017) paper 1, question 19. The student makes the following statements, and again we need to say which of these statements are correct. Statement number 1, in conduction, the conduction band is completely filled with electrons. What we saw in a previous question, a similar kind of statement, that is incorrect. It's only partially full. In insulators, the gap between the valence band and the conduction band is large. That is false as well. It's very small, and that's what allows some conduction to take place at room temperature. In semiconductors, increasing the temperature increases the conductivity. That is correct. If we increase the temperature, we provide the electrons with greater amount of energy in order for them to be promoted into the conduction band. So statement 1 and 2 are incorrect. Statement 3 is the only one that's correct, so that is C. 2017 paper 2, question 14a. Solar cells are made by joining n-type and p-type semiconductor materials. That is a p-n junction. Layers formed at the junction between the materials. That is your depletion layer. A potential difference is produced when photons enter the layer between the p-type and the n-type materials. State the name of this effect. Well, because we're using photons of light to produce a potential difference, this is photo, meaning light, voltaic. (2018) paper 2, question 11c. The student connects a red LED and a blue LED in turn to the battery. The LEDs are forward biased when connected. The student observes the battery will operate the red LED but not the blue LED. The diagram represents the band structure of the blue LED. And we can see in the blue LED we have quite a big band gap here. And that's because if we have a look at the spectrum of light, Roy G. Biv, we can see that red light is at a much lower frequency than blue light. Blue light having a higher frequency, that means there's higher energy. Higher energy means there must be a bigger energy difference between the conduction band and the valence band within the blue LED. You're asked to explain, using band theory, why the blue LED won't operate, however the red LED will. And that's because the red LED has a much smaller band gap, so we have enough energy in order for the LED to be able to move an electron from the conduction band to the valence band and emit it as a photon of light. The electrons in the conduction band in the blue LED don't gain enough energy in order to move towards the p-type material. 2019, paper 2, question 14a. Solids can be categorized as conductors, insulators, or semiconductors depending on their ability to conduct electricity. Their electrical conductivity can be explained using band theory. The diagram shows the valence and conduction bands of three solids, X, Y, and Z. One represents a conductor, one represents an insulator, and one represents a semiconductor. So we're asked to complete a table to show which solid represents a conductor, which represents an insulator, and which represents a semiconductor. Well, first of all, in solid X, we can see there's a very large band gap between the conduction band and the valence band, suggesting that solid X is an insulator. Solid Y, there is a small band gap in between the conduction band and the valence band, suggesting that this is a semiconductor. And then, of course, if we have a look at solid Z, there is an overlap between the conduction band and the valence band, so that must be the conductor. And you'd be expected to be able to recognize as well as draw these diagrams. 2019, paper 2, question 14b. Using band theory, explain why conduction can take place in the semiconductor at room temperature. Well, first of all, within a semiconducting material, we have a small band gap. And because we have that small band gap, some electrons at room temperature are given enough energy to move from the valence band to the conduction band. It's interesting to note that if we were in absolute zero, there wouldn't be enough energy, and therefore this wouldn't happen. So semiconductor materials have a resistance which decreases with temperature, hence the reason why we can use them for our temperature-dependent resistors, or our thermistors. These individual marks are independent, which means either of them would give you 1 mark, but you need both to get 2. 2019, paper 2, question 14c. Silicon can be doped with arsenic to produce an N-type semiconductor. State the effect that doping has on the conductivity of silicon. Well, when we dope with it to make an N-type semiconductor, we're producing an excess of negative charge carriers. That's electrons. If we have an excess of electrons, that means we can have more movement of charge. More movement of charge means more conductivity. It's important to note here that we cannot just accept you saying that this reduces resistance. Although in other past paper questions, the question specifically asked, what is the effect on the resistance of a semiconductor by doping it? Here we are specifically looking at conductivity, because that is what the SQA is asking. 2014 revised higher question 19. Again, we have 3 statements, and we need to say which of these statements are true. Statement 1. In solar cells, a potential difference is produced when photons are incident on the junction. True. The photovoltaic effect occurs in solar cells. True, we saw that in a previous question. In LEDs, photons are emitted from the junction when a current is passed through it. Yes, they are. The current gives energy to the electrons to move from one level to another. That's the conduction band to the valence band. across the band gap, and that means that they are producing light. So statements 1, 2, and 3 are correct. 2013 Revised Higher Question 20. A crystal of silicon is doped with arsenic. This means a small number of silicon atoms are replaced by arsenic atoms. The effect of doping in the crystal is 2. So this is like the other question, except we're specifically looking at resistance. It decreases the resistance. That is, it increases conductivity. 2013 Revised Higher Question 31b. A light-emitting diode LED is a PN junction which emits light. The table gives the color of some of the LEDs and the voltage across the junction required to switch on the LED. So we can see that a green LED requires a switch on voltage of 2 volts, red 1.4 and yellow 1.7. Using this data suggests a possible value for the switch on voltage of an LED that emits blue light. Again, we're looking at our color spectrum, Roy G. Biv. So red here has 1.4, yellow has a switching voltage of 1.7, and green is 2.0. So we can see as we move up the spectrum, that is, as the frequency increases, we're going to need a larger amount of voltage. So really the minimum voltage we're looking at here is going to be 2.1 volts. The SQA is going to accept a range. The upper range has to be realistic. But look, we've got 0.3 of a volt going up from yellow to green. So really what the SQA is looking for is a reasonable range, and they'd accept everything between 2.1 volts and 2.8 volts, and that's going to be inclusive. 2013 Revised Higher Question 31a. Use band theory to explain how electrical conduction takes place in a pure semiconductor such as silicon. Your explanation must include the terms electrons, valence band, and conduction band. Okay, so within a pure semiconductor material that is not doped, we have some conduction take place. And that reason why that takes place is because at room temperature, the majority of the electrons are in the valence band, and only a few are in the conduction band. However, the band gap is small, therefore electrons can be excited to the conduction band from the valence band. Now, when that happens, conduction. So, electrons are given enough energy to cross the band gap between the valence band and the conduction band, at which point conduction takes place. 2012 Revised Higher Question 20. The letters X, Y, and Z represent missing words in the following passage. Solids can be categorized as conductors, semiconductors, and insulators. In X, the energy gap between the valence band and the conduction band is Y, allowing Z conduction to take place at room temperature. Probably got a good idea what we're looking at here. So we're looking at semiconductors. So in semiconductor materials, there is a small band gap allowing some conduction to take place. So we're looking at D. 2014 Old Higher Question 18. A sample of pure semiconductor material can be doped to form an N-type semiconductor. Which row in the table describes the majority charge carriers in the N-type semiconductor, and how the resistance of the N-type semiconductor compares with that of the pure semiconductor? Well, we dope in order to decrease the resistance of the semiconductor or to make it more conductive. When we N-type dope, our majority charge carriers are going to be N-type, that is negative. So straight away we can get rid of D, we can get rid of B. We're looking at negative majority charge carriers. The resistance is going to be less. So the answer is C. 2012 Old Higher Question 30b Part 1. A PN junction is used as a photodiode as shown. In which mode is the photodiode operating? Okay, so here's the negative terminal of our battery, and here's the positive terminal. We can see that our positive terminal is connected to the N-type and our negative to the P-type. which means this is actually in reverse bias. Now, if this is in reverse bias, that means ordinarily it's not going to conduct, because in reverse bias we stretch out the band gap and we make it harder for electrons to make the transition. However, when we provide light, we provide additional energy to the electrons in order to cross the band gap. So that means we allow for a greater amount of conduction to happen. Hence, this is photoconductive. (2012) Old Higher Question 30b Part 2. If the irradiance of the light on the junction of the photodiode is now increased, explain what happens to the current in the circuit. So when we say the irradiance increases, what we mean is that we have more photons per second incident onto the photodiode. More photons per second means more electrons, because one photon goes in, one electron makes a transition. So more photons per second means more electrons per second. More electrons per second means more charge per second. Current is Q over T. It's the amount of charge flowing per unit time. Therefore, if the irradiance of the light on the junction increases, we have an increase in the amount of current. 2011 Old Higher Question 18. In an N-type semiconductor, the majority charge carries electrons. That is absolutely true. The majority of charge carriers are holes. No. The majority of charge carriers are protons. Protons can't move. Absolutely not. There are more protons than electrons. No. A semiconductor is overall neutral. There are more electrons than protons. Absolutely not. So A is your answer. 2010 Old Higher Question 16. An LED is connected as shown. When switch S is closed, which the statement is correct? A. The p-n junction is reverse biased and free charge carriers are produced, which may recombine to give quanta of radiation. Well, that is incorrect, because we can see that this LED is forward biased. We have a negative terminal here, a positive terminal. The negative part of the LED is focusing on the negative terminal, therefore it's forward biased. So this one's also incorrect, and this one's also incorrect. So we're between B and D. B, the p-n junction is forward biased and positive and negative charge carriers are produced by the action of light. No, positive and negative charge carriers are not produced by the action of light. They are already there. However, p-n junction is forward biased and positive and negative charge carriers may recombine to give quanta radiation. Yes, that is true. They may recombine to give photons of light. 2009 Old Higher Question 17. Student writes the following statements about p-type semiconductor materials. Which ones are true? Most charge carriers are positive. Well, p-type, yep. The p-type material has positive charge. No, it does not. Even though it has majority charge carriers are positive, the overall number of protons and electrons are the same. Therefore, the material is overall neutral. Impurity atoms in the material have 3 outer electrons. Well, if I had 3 outer electrons, that means I would have a hole, which is a positive charge carrier, so that is definitely true as well. So statements 1 and 3 are correct. 2009 Old Higher Question 18. A p-n junction diode is forward biased. Positive and negative charge carriers recombine in the junction region. This causes the emission of a photon. And that's us, folks.